Welcome. In this video, we're going to introduce complex numbers. So let's get started. As an introduction, let's consider this equation, x squared plus 1. And let's take a look to see if we can find the solutions for that equation. Well, if we were to graph it, we would obtain this parabola facing up. But now the first thing that you might notice is that this parabola doesn't pass through the x-axis. There is no intersection on the x-axis. So perhaps you might be tempted to say there are no solutions. But notice that this equation is to the second exponent. So according to the fundamental theorem of algebra, we must have two solutions. But our graph is telling us that we have no solutions. So what is the real statement here? Well, let's solve this equation algebraically. So if we would have got this equation, so y equals x squared plus 1, and if we try to solve this, let's just set it equal to 0. And if we solve this, we're going to get, well, let's subtract 1 to both sides. So we're going to get x squared equals negative 1. And if we take the square root, we're going to take the square root, so plus or minus the square root of negative 1. So algebraically speaking, we have this statement. But notice that there is a problem here, because we're taking the root, or the square root of negative 1. And that's a problem, because there is no real number that will satisfy this condition. So how do we know what are the roots? Well, the square root of 4 is 2. But why do we say that the square root of 4 is 2? Because notice that 2 to the second is 4. The square root of 9 is equals to 3. But why is that? Because 3 to the second, it is 9. So now what we're essentially doing here, we're trying to say, well, what number to the second exponent is equivalent to negative 1? But notice that there is no number that satisfies this condition, because any number, if it's positive or negative, if we raise it to the second exponent, it will always be equivalent to a positive. And here we're saying we're looking for a number that if we take the second exponent, it is equivalent to a negative. And there is no number that is satisfy this condition. So there is no real number. So there is no real number. And by real number, I'm using the numbers that are in my number line, all the way from negative infinity to positive infinity. So we know that we cannot use real numbers to properly solve for this. So how do we actually come up with a solution for this statement? Well, we introduce a new kind of number. And that new kind of number is what we call a complex number. And before we introduce a complex number, we have to properly discuss what is this expression, square root of negative 1. Well, the square root of negative 1, that is going to be equivalent to what we call an imaginary number, which is just an I. So now in mathematics, whenever you see an I, that implies it is an imaginary number. And imaginary numbers need to be introduced whenever we have square roots of negative values, or any kind of roots of negative values that will not satisfy a certain condition. But this is how we're going to be defining an imaginary number. An imaginary number, it's equivalent to the square root of negative 1. So therefore, if we come back to this equation, now we have two solutions: the square root of negative 1 and x equals the negative square root of negative 1. So therefore, we still have both of our solutions, which is positive I and negative I. So notice that we have not violated the fundamental theorem of algebra, because we got two solutions. If we come back to our introduction problem, we definitely have two solutions, I and negative I. But those solutions are not real. They're what we call imaginary numbers. And that also goes hand in hand with how we graph our equation, because by the graph, it doesn't touch the x-axis, so therefore there are no real solutions. We know that we must have two solutions, so both of them must be imaginary. Now this imaginary number, or I, which is derived by the square root of negative 1, it has certain properties, and let's discuss some of those properties. The first property that we're going to be discussing has to deal with exponents. So if it's a number, we can definitely introduce some of the operators that we know: multiplication, addition, division, and so forth. But let's see what happens when we start looking at exponents of those so-called imaginary numbers. Well, the first case is if what is I to the first? Well, I to the first is just I. So we can say that I equals I, which is just trivial. Anything it's equivalent to itself. But now, what exactly is I to the second exponent? Well, I to the second exponent, that's equivalent to I times I. But notice that we do have an expression for this I. Remember that I, it is derived from the expression square root of -1. So now essentially what we have is square root of -1 times the square root of -1, which is equivalent to the square root, or the square of the square root of -1. And the second exponent is going to cancel out with the root. So now we know that that's equivalent to 1. So that's a new expression here. Now what we have shown here is that I to the second exponent, it's equivalent to a real number, which in this case, it is -1. And we're going to be using this property a lot throughout our classes. I to the second, it's equivalent to a real number, and that real number, it's equivalent to -1. So what is exactly I to the third? Well, I to the third is I to the second times I. But notice that we already know what I to the second is. I to the second is -1. So now we have -1 times an I, and that's equivalent to -I. So that's another characteristic. I to the third is equivalent to -I. Well, let's see. What is I to the fourth? Well, I to the fourth is I to the second times I to the second. But we know what I to the second is. We have an expression for that. We know that I to the second is -1. So therefore, if we come back here, we're going to have -1 times -1, which is essentially just +1. So here we have another characteristic. I to the fourth, it's equivalent to +1. Now let's just do one more example. So what is I to the fifth? Well, I to the fifth can be seen as I to the fourth times I. But I to the fourth is equivalent to 1. So we have 1 times I, which is just I. I to the fifth is just I. And you will notice that this cycle will repeat itself. I to the fifth, so everything is going to be repeated between the expressions I to the first to I to the fourth. Those are the most important ones. So let me just highlight them. Because anything beyond I to the fourth, we're just going to repeat these expressions, because now I to the first is going to be I to the sixth is going to be -1. I to the seventh is going to be I to the eighth is going to be +1. I to the ninth is I. So everything's just going to be going on as a cycle between these two expressions, between I, -1, -I, and +1. But these are the most important ones, because this is, you can think about it as a cycle. Any exponents beyond to the fourth is just a cycle between these two results. I'm sorry, these four results. So now that we have discussed some properties about the imaginary number, now we can properly define a complex number. A complex number, it is a number which is made out of a real and an imaginary part. And the standard form has the following form: a plus bi, where a and b are real numbers. So a complex number, it is a number that is composed of two parts: the real part, and the reason why we call it the real part is because there is no I on it, it's just a real number, and this is called the imaginary part. The reason why we call it the imaginary part is because notice that the second term here, it uses the I, which is the expression that we use for imaginary numbers. So a complex number, it is a number that is made out of two numbers: a real number and imaginary number. So what are some things that we can do to this complex numbers? Well, if it's a number, we can definitely perform addition and subtraction. But how do we add or subtract complex numbers? Well, let's take a look at A. The first thing that you want to take a look at A is that we're adding two complex numbers. This is my first complex number because notice that this whole thing is a number. It is the real part and the imaginary part. And here we add in another complex number. Here's the real part. I'm sorry, here's 2 is the real part and 3i is the imaginary part. So here, instead of looking at it as 4 terms, you can think about it as if it was 2 complex numbers. So how do we properly add complex numbers? Well, whenever we adding or subtracting, what we want to do is you want to add and subtract like numbers. And what do we mean by like numbers? Well, just whenever you're simplifying expressions and they tell you to add and subtract like terms, that's what we mean by like numbers, are reals with reals and imaginaries with imaginaries. So reals with reals and imaginary with imaginary. But what do we mean by that? Well, going back to example A, let's drop the plus sign. So we have 3 minus I plus 2 plus 3i. So what are the real numbers of this expression? Well, the real numbers are 3 and 2 because they don't have an I on it, so they're real. So if I combine them, I get a 5. So this is what I mean by combining like terms. Reals with reals. I added a real with the other real. Now, let's add up the imaginaries. Well, notice that now we have 2 imaginary. I have negative I plus 3i. Well, think about it this way. I have 3 i's and I take away one of them. So how many i's do I get at the end? Well, I just get 2 i's. And that's it. In order to add or subtract complex numbers, all we got to do is you want to combine like numbers, reals with reals and imaginaries with imaginaries. So let's just do example B. C and D, we're not going to discuss it. Now, example B, it does have a negative sign on it. So this just tends to be a little more tricky. What we want to do now is we're going to take a look at the first parenthesis or the first real number. So that is 1 plus 2i. And now notice that this negative, it's affecting the whole parenthesis. It's affecting the whole number. So how you can think about it is that this negative, it gets distributed. So all we can do is just switch the sign of those numbers. So now that becomes a negative 4 and a negative 2i. Now that we have it in this form, there's just a bunch of terms. So how do we combine them? Like numbers, reals with reals and imaginary with imaginary. So let's identify the real numbers. So here the real numbers are 1 and negative 4. So if I combine those real numbers, I'm going to get negative 3. Now, what about the imaginaries? Well, I have 2 imaginaries. I have 2i and negative 2i. Well, if I have 2i and I take away 2i, I have 0 of them. Or in other words, I have 0i. So this is my result. Or we can just rewrite this as just positive 3. Either or. Now, this brings me to my next discussion. We can make a claim that all real numbers are complex numbers because a real number, in this case, negative 3, it is definitely a complex number, but it is a complex number where the imaginary part is equivalent to 0. And that's just a small little technicality that we do have in mathematics, that real numbers can be categorized as complex numbers, where it's just a complex number where the imaginary part is 0. But this is just 2 small examples that I just used to illustrate how we can properly add or subtract complex numbers. So now the next operator that we want to discuss is multiplication. How can we properly multiply complex numbers? Well, for that, we're going to take a look at A, B, and C. So for example A, notice that here we have a complex number. It is a complex number whose real part is -2 and the imaginary part is 3i. And what we want to do to this complex number is that we want to multiply everything by 5. So how do we do that? Well, it's just a simple algebraic procedure. We want to distribute this 5 to the values that we do have inside the parentheses. So now that becomes -10 plus 15i. And that's our result. For example C, notice that what we're doing here, we're multiplying two complex numbers. 3 plus 2i is my first complex, and 3 minus 2i is my second complex. So how do we multiply complex numbers? Well, you're essentially multiplying two binomials, so we're just going to multiply those binomials. So let's distribute. So 3 times 3, that's 9. Oops. That's 9. Distribute one more time. So now that becomes -6i. We distribute this, so now that becomes positive 6i. And now we distribute this, now that becomes -4i squared. And just like we did before, I want to add and subtract, so I'm just going to add complex numbers with real numbers with real numbers and imaginary with imaginary. I can see that I have two imaginary parts, so let me combine them. -6i plus 6i, they're going to cancel each other out, so we have 0 i's. So let's just bring this down. So we have 9 minus 4i squared. Now, you might be tempted to just call this your final conclusion, because notice that we have a real minus an imaginary. But this imaginary is raised to the second exponent. And whenever we want to write down just complex numbers, the i's should be written on the first degree, or we want to simplify it as much as possible. So we have to deal with this I to the second exponent. But notice that we have an expression for this I to the second exponent business. We have just shown that I to the second is equivalent to -1. So therefore, we can just substitute this expression by just -1. So now my problem becomes 9 minus 4 times -1. And if we do this correctly, we're going to have 9 plus 4, which is essentially just 13. So notice that whenever we're multiplying complex numbers, we might end up with imaginaries to a certain exponent. And whenever we have that, we want to think about the results that we have properly come up in our previous discussion a couple minutes ago. So examples E, B, and D, we're not going to discuss them. I can just let you try those as an exploration or as a practice problems. The last thing that I want to discuss whenever it comes to complex numbers is something that we call the complex conjugate. So the complex conjugate, it's a number, but it's a number that has been defined by a complex number. So what do I mean by that? Well, if A plus BI, it's a complex number, which notice that it is, then the complex conjugate is defined as A minus BI. So to properly define the complex conjugate, all we do is we switch the sign of the imaginary part. So if you have a number, let's just give some examples of this statement. Let's assume that we have a complex number, A minus 2I. Well, the complex conjugate is going to be defined as 5 plus 2I. Let's give another example. Let's assume that we have a number, 3 plus 20I. Well, the complex conjugate is going to be defined as 3 minus 20I. And what is the complex number so important? Because let's go back to example C. If you take a look at example C, we have a complex number and we multiply by its complex conjugate. And anytime you have a complex number and you multiply by its complex conjugate, what you're going to end up with, it's always a real number. That is always going to be the case. Any complex number multiplied by its complex conjugate, the result, it's always a real number. So keep that in mind. It's not that we're just creating new numbers and then put a fancy name on them like the complex conjugate. We create those type of numbers because we want to create a number that can give us this property, a property where if I multiply a number by this so made up complex conjugate, the result it's always going to be a real number. So keep that in mind. And with this, it concludes our lesson for the introduction to complex numbers.